Hi, Professor and TAs. Thank you for watching my final report of system engineering. My topic is about autonomous vehicles. It is a very good choice. I was very interested in this topic since I was a child. Now I first want to invite you to watch this very interesting short video of autonomous vehicles. Now switch from autonomous vehicle to manual override. This comes from a video called I, Robot from 2004. I was a young child when I first shocked how a vehicle in this movie works. We can see that there are two kinds of autonomous vehicles in the video. One has human passengers and another is absolutely unmanned. And in this research, we will discuss the first kind with human passengers. We can see that it can drive itself, and in case of emergencies, the human driver can take over full control from the system. And this imaginary vehicle is a glimpse of the future. So, first is the background of autonomous vehicle. Why do we choose autonomous vehicles? This is a very good question. According to the numbers, 1.2 million people die in traffic accidents every year in the world, and this number is still rising. About 94% of traffic accidents are caused by human factors. By 2030, which is less than 10 years from now, 5 billion people around the world will live in cities. And the global car ownership will directly double from the existing 1.2 billion to 2.4 billion, which means the problems such as traffic congestion, safety, and carbon emissions will become much more prominent. It is estimated that if all the vehicles in the world are replaced with autonomous vehicles with intelligent perceptions and coordination capabilities, humankind can avoid at least 1 million deaths in traffic accidents every year, reduce the auto carbon emission by more than 10%, and save this part of fossil fuel, which is, avoiding shortage of oil. Autonomous vehicle system dates back to 1920s and 1930s, with the first truly autonomous vehicles appearing in the 1980s. Since the mid-1980s, many universities, research centers, and companies around the world have been researching and developing autonomous vehicles. In 1984, Carnegie Mellon University promoted the NavLab program and the ALV program. After the 21st century, fully autonomous vehicles have been manufactured on test vehicles, and Tesla cars are the best and the first to launch. Autonomous vehicles is in specific environment. From now on, we will carry out need analysis on autonomous vehicles using system engineering knowledge. From the perspective of engineering, using operations analysis, we can find a list of operational objectives and system capabilities, which includes the several major needs of the current users for autonomous vehicles. The first is, of course, autonomous driving, and it includes several parts, but we unite them as one function, one subsystem, which includes autopilot, level L2, and road and obstacle identification, vehicle compute power, and path planning, direction control response, barriers to bypass, and autonomic braking. That's emergency braking. I'm sorry. The second one is a high level of safety, which means the autonomous vehicle must be much safer than human drivers. We as humans are not fit to drive, to focus the same time, you know. And the third one is acceptable price, which means you cannot be much more expensive than the average car price. You have to be affordable to most of the people. Great. So in the functional analysis stage, we can find the following required functions. Autonomous vehicles would be a vehicle that looks like a traditional car, but only looks like. The main function is to provide a certain degree L2 or L3 level of autonomous navigation for passengers or drivers, improve the identification of roads and obstacles, path planning, direction control, autonomic acceleration and deceleration in the range of 0 to 200 kilometers an hour, obstacle passing, emergency braking, and other autonomous driving functions. And of course, it must be able to provide the passenger or drivers with similar driving services as human drivers. Autonomous vehicles should be able to use onboard computers to determine in real-time factors that may pose risks to the passengers, pedestrians, and others, and take reasonable measures to avoid obstacles in advance. Autonomous vehicles should have a similar price range to passenger cars, which is usually between $10,000 and $100,000. According to the function needed, and as we analyzed, we know there are three kinds of needs must be met. First is autonomous driving, second high-level safety, and third is acceptable price, as we mentioned before. And therefore, using feasibility definition, we can conclude that the main components of an autonomous car includes the engine, or electric motor, battery system, and electrical system, frame, suspension system, passengers, compartment, interior, etc. Of these are all the same or similar with the ordinary cars, and we are not going to discuss them in detail. And what we are going to discuss is those subsystems that only the autonomous vehicle has, and those are vitals to the autonomous vehicles. So those includes onboard radar, onboard camera or cameras, and powerful onboard computer, high precision GPS system, real-time networking system, directions and acceleration and deceleration control system, etc. These can be summarized into, as you can see, three major parts. The first is environment perception system or perception system. The second is recognition and decision-making system. Sometimes this is divided into two, but those are all software on the onboard computer, so we can make it one. Those are all algorithms, you know. The third one is, of course, motion control system, which does what the computer tells the car to do and transfer them into real actions. And of course, other systems like normal cars, which we will not discuss in detail in this presentation. And in short, in this in the need validation stage, we analyzed and concluded that the needs are valid and can be met. We should be able to engineer an autonomous vehicle that that meets our numbers. This is a typical hierarchical topology of autonomous vehicles. And this is the basic topology connected to the hardware and software of autonomous vehicles in the form of a diagram. Now, in the concept exploration stage, considering about the requirements and constraints and system materialization during the system lifecycle, we aim to find the suitable engineering alternatives for the system. Different subsystems of the autonomous driving system have multiple sets of available solutions, like every engineering practice. The difference in the mainstream technology routes mainly reflects the differences between the environment perception system and the vehicle intelligent identification, path planning, and vehicle control system algorithms, which these includes three parts, as we mentioned before. So the first is alternatives for environment perception system. These are vehicle wave radar system and ultrasonic radar system, LiDAR system, visible light camera systems, and high precision GPS, inertial navigation, high precision maps, and of course, in order to communicate, we need Internet of the vehicles or their hybrid systems. The second part is recognition and decision-making system. Their alternatives is powerful computer, onboard computer, and algorithms. In short, for details, you can check my written report. And the third part is motion control system. Electronic motors and hydraulic parts are usually the alternative that we would adopt. And just to be clear, autonomous vehicles, they are vehicles. They still have the main parts and traditional subsystems as normal vehicles are. These traditional subsystems and desires will be included in the final report of the engineering exploration. Now that we have discussed the alternatives for the subsystems and components parts, here we have a graph showing the three stages of autonomous vehicle technology development. We can see that in history, these and industry companies went through the process of long time exploration and trying out, just like we analyzed. Now we have got to the concept definition part. In this part, we will choose the finest alternative and give the definition of them. For detailed discussion can be seen on the written report. And due to time restrict, we won't go through the discussion in detail. I can see I have only 1 minute left. Oh well, maybe I need more. We choose radar with cameras over LiDAR to be the environment perception solution. Because for radar is the most reliable technology, detecting the distance, range, and motion characteristics of objects in almost any condition. It uses reflected radio waves to detect obstacles behind other obstacles and requires less signal processing. And for LiDAR, LiDAR is a new technology, but LiDARs, they require much more power and compute power and an enormous storage room. So LiDARs, they are now basically they are used for test cars or luxury cars. For ordinary civilian vehicles, we should choose radar and cameras over LiDAR. Sometimes some companies, in order to save the money, to lower the cost, they choose camera systems with 8 to 6 cameras around the car, like Tesla. Tesla, they don't use radar or LiDAR, they use cameras only. Now, the second is route planning and motion control. Algorithms, I cannot visualize algorithms, so I use these pictures. You can have a better idea of it. Route planning is the real-time calculation of the data returned by the sensor, which is radar and cameras, by the onboard computer. The computer processes it, and the overall route and short distance route are planned according to the destination or preferences. Route planning can be optimized by upgrading after the vehicle is put into use, which means you can even replace the algorithms. You can even replace the whole system to a better use level. We can get a better system, a better perception, and a better algorithm system after we have been using the car for a few years. And motion control involves the fine control of moving parts of the vehicle control system, which is generally completed by high precision motors or hydraulic moving parts. These are basically the same, or they're the same stuff with the traditional cars, because in traditional cars, you have the motion adjustment system. It's autonomic, and it can do some tiny fine adjustment for the human drivers, sometimes to keep the car in a direct line when you're in the highway. So these high precision motors and hydraulic moving parts, they are the same with the traditional car parts. They execute real-time commands from the onboard computer. Now, after discussing the technical development route of autonomous vehicles and alternatives of various subsystems, as well as investigation of autonomous vehicles in the market, our preliminary selected technical solutions are vehicle cameras, radar as environment perception system, and building machine learning algorithm in the vehicle computer, which is very powerful computer, as identification and path planning algorithms. The infrastructure of conventional lithium battery electric vehicle is used, which means the autonomous driving vehicles, they are mostly vehicles with batteries. They need a powerful power supply, which is better installed in the electric cars. Oh, sorry, I discovered that I forgot to flip the PowerPoint. So now this is the visualization picture of machine learning driving pattern. Is for algorithms, and this is the topology that we choose: an autonomous vehicle with radar, LiDAR, camera. No, we don't want LiDAR. We want radar, cameras, and front cameras, and cameras around the car, and GPS, and of course AI driving system. As for the assessment, at this stage, this technical concept has been demonstrated by some major auto manufacturers. among which Tesla uses pure visible light camera as environment perception systems, and Toyota, Honda, Lexus, and other manufacturers use a mixture of radar or LiDAR and cameras. Various manufacturers have developed core algorithms for autonomous driving based on machine learning algorithms. Almost all of them are based on machine learning, and therefore we can conclude that the technical risk of this engineering and technical concept, which is autonomous vehicle, this is relatively small. The risk is relatively small, and the commercial risks depends on the technical strength and production and sales capabilities of the participating companies. For the detailed definition of terms like radar, LiDAR, AV, please refer to my written report. The next is engineering development stage. It includes advanced development, engineering design, and integration and evaluation. First, in the advanced development stage, we need to analyze and solve as many uncertain factors as possible, so as to output stable design specifications and models. Therefore, we need to consider many factors and analyze the uncertainties. First is high technical requirements. These include route perception technology and automatic control technology, human-computer interaction technology. Second is that there are some huge design challenges. Autonomous vehicles need to work in a variety of road environments and conditions, which includes handle all kinds of weather conditions and handling complex traffic situations. And third is safety, of course. Autonomous vehicles must be safe in all situations. So software and hardware safety and system reliability and personnel safety should be considered, including system reliability and personal safety. Fourth is law and regulations. Variety of vehicle safety laws and regulations. There are road traffic laws and special regulations for autonomous vehicles only. And the last uncertainty is market demand. Using the method of requirements analysis, function analysis, and design and system engineering, we need to analyze the study and uncertain places in the system. First of all, based on our analyze in the previous stage, we have selected the following technical solution, which is including onboard camera, radar as the environment perception system, and machine learning algorithm built into the onboard computer as the identification and path planning algorithm. And the basic algorithm is the basic architecture of traditional lithium battery electric vehicles. Since the main subsystems of the autonomous vehicle have been transformed to some extent, we need to carry out advanced development of these systems. The first is environment perception system. So we can see that it is the core system of the autonomous vehicles and the very important system, which is responsible for collecting and analyzing surrounding environment information and converting it into data that can be understood by the machine. Therefore, special attention should be paid to the performance and reliability of the environment perception system during testing to ensure that the vehicles can correctly perceive the surrounding environment. There are two kinds. The first is LiDAR and the second is a visual camera system. They are both very cheap, mature, and widely used. For more detailed information, please refer to my thesis of the following parts. And the second is decision-making system, which is this one. It is the intelligence center of the autonomous vehicle. The maturity and stability of the decision-making system depend on the robustness and performance of the onboard computer, mostly of the chips, the CPU and GPU. At present, the onboard computers of self-driving vehicles are generally equipped with powerful chips, which are proved to be stable, powerful, and mature. The third one is control system. So the control system is the execution center of the autonomous vehicle, which is responsible for controlling the vehicle power system, steering system, and braking system according to the instructions of the decision-making system. So it is well developed. It's been developing for decades and mature and durable. Now, through the analysis of the system engineering methods by advanced engineering, we can determine that the system design specifications of autonomous vehicles, it should be as follows. The first is system overview. So it refers to a vehicle that is similar to the appearance and function to an ordinary family car, but has at least L2 level autonomous driving function. The second is design requirements. From the point of view of system lifecycle, within the whole lifecycle of the car, it should have the autonomous driving capability of L2 or above. The third one is system architecture. The system should have several subsystems, such as frame, chassis, power system, environment perception, decision-making system, and control system. The fourth is system reliability. In line of the International Standards Organization on the Automotive Industry Quality System Standard, ISO TS. And now we have the validated model. Through the system engineering method and analysis of advanced engineering, we can determine the model of autonomous vehicle system design, which is on the basic model of traditional electric vehicles with at least L2 level of self-driving function. And it should be equipped with environmental awareness system, decision-making system, and control system. These systems are based on the next is engineering design stage. For engineering purposes, we should pay attention to reliability, maintainability, and productivity. And the produced system, which is autonomous vehicle, must have an accepted short mean time between failure, which is MTBF. Therefore, I think the engineering design of autonomous vehicles should strive to achieve a few characteristics, which are so these characteristics should be, the first is minimize interface between subsystems and components. The second is key subsystems should have redundancy and of different inputs. The third is fully consider the reliability of human operation. The fourth is maintenance simple, modular design, and replaceable unit. The fifth is it can produce in large quantities and reduced cost. According to the requirements of reliability, maintainability, and productivity, we conducted the following analysis. First is key subsystems should have redundancy of different inputs. Multiple redundancy mechanisms can be designed for key subsystems, including software redundancy, hardware redundancy, information redundancy, and these are for ensuring system reliability. The second is to consider the unreliability of human operation. Design proper transfer mechanisms. Autonomous vehicles should have proper transfer mechanisms that follows the driver to easily take over the control of the system if necessary. The third is maintain a simple modular design and replaceable unit. By using modular design, the system can be divided into several independent modules, making maintenance easier, and use standard interfaces. By using these interfaces, you can make the connections between modules easier and improve the maintainability of the system. The last one is it can produce in large quantities and reduce costs. In addition to using modular design, standard design method should be used. By using a standardized design method, design workload can be reduced, and standardized parts can be used to reduce production costs. Through the previous analysis, we know now that there are some specific requirements of this stage of engineering design, so that we can infer which specific parts and subsystems may have instability and risk based on these requirements. We can propose the following test requirements to provide reference for the next stage of testing. And you can see that I've divided them into these three aspects: reliability, maintainability, and producibility. And they have very detailed, small requirements. I like them very much. Now, the main components of an autonomous vehicle includes the engine, the battery system, electrical system, frame, suspension system, passenger compartments, interior, etc., as well as onboard radar, camera, and powerful onboard computer, high-precision GPS system, real-time networking system, and which are not available in the ordinary cars. These can be summarized into 4 subsystems. In more detail, the prototype of this autonomous vehicle was studies should consist of the following parts. And we can see that the prototype have the parts that are the same as conventional cars, ordinary cars, and the parts that is unique to autonomous vehicle. And this is a very detailed chart. This is the topology of engineering prototype. The next is integration and evaluation. Now we are putting the parts together and testing them. And during the evaluation phase, the entire system is tested to evaluate the performance indicators such as functionality, reliability, maintainability, or so on. And these tests can be mock or real tests. Based on the test results, system engineering can make adjustments to improve system performance and reliability. It includes integrate all subsystems together, conducts tests, and evaluate and verify the performance, then debug and document this test process. After analysis, we come to these detailed test requirements, including simulated test and field tests. So this is the simulated test. And field test is that you run it on the road. Simulated test is that you run it on the on a computer, a system. It's a virtual simulated test, or you can run it on the testing field. And before that, we should test the subsystems and components, just like we did on the last parts. Now, when it comes to testing, there is a very important thing that is called scenario. Scenario is the most important step in the automatic driving testing system. So we should try our best to ensure that the automatic driving test scenario is practical and realistic, and let the test system accept the test of various and many kinds of scenarios. From the perspective of scenario structure, there are different driving occasions, such as highway, rural roads, urban conditions, and airports, docks, closed parks, and open roads, and so on. So in this case, how to drive and the driving task, the driving speed, the driving mode, and so on constitute the three-dimensional architecture of the whole scenario. These are two pictures of the two kinds of tests. The first is simulated virtual test, and the second is field test or road test. But obviously this car here is a testing prototype. It's not the car that we want to sell. It has these parts attached to it. And the next is post-development stage, which means we have done designing and putting on prototypes. Now we want to produce them and operate and support them, which is selling them. So this stage includes production, operation, and support. Now we have a perfect car as a prototype. So how can we put it into production? As a system engineer, it is not a smooth ride. We all know that, from development to production, especially when it's something complicated like a car. The production of a prototype machine and the production of a factory assembly line are two very different systems. Although we have tried our best to consider the convenience and efficiency of the production in the design stage, but still we need to carefully follow up and plan the transition process and the production and delivery of the onboard computer chips, like COVID-19 response policies in the country. So what we are talking about is the problems that we might face in the transition. Communication issues that may arise during the technology introduction process, and differences between assembly line design and production of prototypes, and differences between products from with components from different suppliers. These are all very severe problems that we have to face during the transition to production. So I've missed that the participants of the transaction. So this part is almost all the same with any other kind of product. You know, the system engineer, the senior technical personnel of the factory, etc. Next, now we have to go through a few stages to manage the offset of the production at the factory, including, now we can see that, including planning the layout of the car production line, determine the production process, prepare a production plan, make overall production plan, and design the production management system, establish quality assurance systems, safety management system, and human resource management systems, and establish a supply chain management system, which is very important because the suppliers, they supply important components and parts of your products. So the reliability of their product directly influence our product, right? Now, conduct trial production. So we can see that this is a streamline. This is a production line. So after producing the trial production, we test the parts and vehicle quality and gradually debug the production line and various technical equipment and gradually increase the production capacity after reaching the standard. As a manufacturer, after production, operation and support are very important too. First is to provide detailed car instructions. Establish fan community and write a very good user manual and create a very good fan culture for users, which will give the users and fans some place to talk about tips. Second, we should build a perfect after-sales service network so that the consumers can conveniently enjoy professional after-sales service. After-sales record system and reasonable warranty policy systems and warranty networks should be established as well. There are some pretty huge challenges for system engineering during this whole process of project. So there are problems like complex system architecture and high demand of robustness and compatibility issues. Full life cycle reliability is required as well. Safety perception systems are not perfect, and need for high precision maps, satellite navigation, hive communication technology of internet of vehicles, data security. These are all very big problems. And at last, there is a human-machine cooperation needs. So still there are some social acceptance problems and legal risks. For more detailed explanation of challenges, please refer to my written report. And this project is a case study on autonomous vehicles. In short, it uses the analysis method of system engineering through concept development stage, engineering development stage, and post-development stage. And the system model of autonomous vehicle is analyzed and constructed from scratch. This is a project that contains examples of several car brands and types, like Tesla. So after a master's study and this case study project, I fell in love with this course of engineering, of system engineering, which is very suitable for me to give full play to my characteristics of wide range of knowledge, strong overall perspective, and good organization and coordination ability. For example, in this case study project of autonomous vehicle, we must use rigorous system engineering methods to conduct demand analysis, function analysis, concept definition, and other work on the research object. Comprehensively apply a variety of systems engineering analysis methods. Through in-depth research, a lot of literature reading, and rigorous analysis in order to establish a perfect system model so as to design a good product. My understanding of system engineering have also been greatly improved. I realized that the system engineering is not only about how to design and improve systems, but also about how to use engineering methods to solve practical systems. I also feel that the wide application of system engineering, which can be used in various fields such as transportation, manufacturing, civil engineering, and information technology, and so on. So system engineering is very good subject. At the same time, it is a very complex subject as well. It contains a lot of complex knowledge, but at the same time, system engineering is an art, just like the professor said. An art about bigger picture and trade-off. I think Professor Zhu's example of performer and conductor of a concert is the most appropriate example of system engineer. It's not the conductor's job to play the violin, nor is it to play the piano. His job is to know the whole picture of the musician, of the concert, and to conduct perfect concert. Last but not least, I would like to express my sincere gratitude to the professor and the TAs. Thank you so much for all the knowledge and help you gave us. This has been a great journey. So this is my final presentation. Should anything be changed or any way to improve it, please do not hesitate to enlighten me. Thank you so much, and goodbye.